All right, so our next piece to look at is what we call a phase diagram. And so we're going to be looking at our three kind of major phases for a substance, and how we start to describe those phases in relationship to their temperature and their pressure. And this is a pretty typical phase diagram that you will see for most substances, with one notable exception. We'll look at that here in just a second. But this is how we start to describe our different substances. And so if we're thinking about our labels on our axes, very good ACT style questions. Here we've got a low pressure, a low temperature. We're increasing temperature from left to right. We're increasing pressure from bottom to top. So if we're just thinking real low temperatures and high pressure, so we've got really, really low, slow-moving particles, and we've squeezed all those particles together, we're going to end up with our solid substance. Got a solid substance. On the other hand, if we had very, very low pressure, no hardly any pressure, we pull a vacuum on there, and we heat up the particles, they're going to move faster and faster and faster. Here's our gaseous phase. Here we'd have our gas region of our phase diagram. And then in between a solid and a gas at medium temperatures or medium pressures, well, that's going to be our liquid phase. And so we're just describing where we are in terms of our different substances in relationship between their temperature and their pressure. And this is actually one of those things that we can start to use to describe the strength of the attractions of our particles. Because we know that if the attractions of our substance are higher, our boiling and melting point become greater. It takes more energy to get them to split apart. And so we can actually see a change and a shifting on our phase diagram as a result of that. Now there's a couple of important spots here to think about. What would this boundary line be here? To go from a solid to a gas? Oh, well that would be sublimation. Our dry ice will go directly from a solid to a gas at lower temperatures, and slightly higher, at lower pressures and slightly higher temperatures. If we're thinking about going back the other way, there's a term for that. It's called deposition, to go from a gas back to a solid. If we're going from a solid to a liquid, well, this would be melting, right? We would heat up the temperature to melt our substance to get it to turn into a liquid. We could also increase the temperature enough to get our liquid to change into a gas if we're going from here to here. Well, it also turns out that you can change the pressure. If you take your substance and you decrease the pressure, you can get your liquid to go from a liquid to a gas by altering our pressure. And so changing our phase boundaries, solid to liquid, that'd be melting. Liquid to gas, that'd be vaporization or boiling. Going back would be condensation, and then freezing, going back the other way. Now, but there's a couple of pieces here that we gotta kind of call our attention to. There's this little spot right here in between all three of them. We call this the triple point. This is the triple point. At this particular point and spot, you theoretically could have any one of the different phases or all three of the phases existing at the same time. Now, it's really hard to kind of see that, right? Because what are you looking at? And typically, when we think about changing these constants, we're going from one to the other. But theoretically, there is a spot where all of our phases exist kind of co-equally, and that would be our triple point. Way up here, we got another spot. Call this the critical point. Critical point where we can no longer distinguish. When we reach this point, we can no longer distinguish. We just actually can't tell whether it's a liquid or a gas. It becomes indistinguishable. We can't tell anymore because we're unable to observe the particles to see what they're doing at that particular point in time. And so by kind of altering our conditions, either a temperature or a pressure, we can actually start to change our different phases. Example real quick for you. We got some butane here. I guess if we wanted to see, well, this is going to be easier. If we've got liquid butane, so our lighters usually come in sealed pressurized containers. Oh, so we have a higher pressure, and so in our butane, we've got liquid. When we release under atmospheric pressures, we kind of press down the little fuel injector or the fuel tab. It releases the liquid, and because we now have a lower pressure, the liquid changes into a gas, and that's why we then have our butane lighters. So that's kind of going that direction. But that would mean that theoretically, you should be able to go the other way, that we should be able to take the gas. We'll see if we can get a good enough resolution here. So I'm just taking some butane and I'm putting it into my syringe here. So now I have a syringe full of butane. I'm going to go ahead, and you're going to want to look right at the tip. Hopefully our camera quality is high enough. There should be a moment where it goes just slightly translucent, where we can actually get, oh, there, we'll start to see kind of the condensation. We see liquid droplets. Oh, there's one right there. Real good liquid droplet right there where our butane is being forced back into its liquid phase. And then the gas, of course, wants to re-expand. And so what we did was we took the gas, we increased the pressure and forced it back to its liquid phase. And so we can actually change our properties one of two ways. And to prove that, yes, it is in fact, oh, nope, ran out of juice. It is in fact butane that we used in here to cause that effect. Now, there's one notable distinction I'd like to make for these phase diagrams, and that is our water. Our water is weird. Our water is weird. The line for water, for H2O, dihydrogen monoxide, it tips back. And what this means is two things. That by applying a pressure, you can actually get solid water, ice, to become liquid. This is how ice skates work, right? It's not that you're actually like cutting the ice apart, right? No, it's you are forcing all of your pressure into a fine point. That pressure is then causing the ice to turn into liquid, and you glide across a thin strip of liquid water. And so this tells us that there's actually room between the solid particles to become more dense. We're actually going to squeeze the solid because there's empty space. That's why ice floats, right? It's less dense. Solid ice is less dense than our water. We can actually squeeze the solid water, decrease its volume, and change that solid into a liquid. It's a unique property that water has that is actually very abnormal when we think about most substances. Most substances are a solid, and our solid is more dense than the liquid. That is not the case for water. And that actually gets exhibited in our phase diagram with this kind of backwards line on our phase diagram. Cool. So using this type of information, you can start to kind of glean out differences in terms of their intermolecular forces and describing how we start to change phases from one substance to the next.